So after lunch, everybody is free to go and, enjoy the Friday.
Yoo-hoo!
All right. So Cristina, thank you.
Okay, so thank you. I have this thing to have to give the last lecture of the 2 weeks of lectures, so you guys are fed up. So I hope that you keep a little bit of energy for this, okay? For each lecture, I have like a little title, remember. Now, and this one is Stars from Away Are Found Here. From Far Away Are Found Here. So essentially, we had these 3 lectures, and we are now today talk about the supermeteor-rich stars. So yesterday, we saw the bulge, and we said that many of them can be found here. We saw some of them here, a little bit, but now we'll see many, okay? And then, of course, we will look to future things that are being made, which you guys are the ones that are going to use. Okay, so the first point that I wanted to make, and this is the main point, is that even when you are in a very local volume, so instead of, we were covering at some point with apogee 20 kiloparsecs, remember? The whole disk. Now, for the first time we had sorry, today I'm a bit slow. I drank too much yesterday. So it was my birthday and I exaggerated. What I want to say, yes, so the Hipparcos astrometry was in 100 parsec, so really small, right? Yesterday we saw some supermeteor-rich in 1 kiloparsec volume, right? So even in this 100 parsec volume, we have stuff that came from other galaxies and from the bulge. It's amazing, okay? And that's what we are going to see now. To do that, we made a proof of concept paper, which is this one of Friedrich et al. During his PhD thesis, where we decided to use a very, very high quality sample. So if you are so close by, there was a very nice spectroscopic survey that's called the HARP sample. And it's very high resolution spectra. And when you have high resolution spectra, you have a lot of chemical elements, okay? So you don't need to be in this alpha over iron plot that we talk so many times. You can go on to other chemical elements. But then you have another problem. You have such a large dimension problem that you need help. And machine learning is becoming this help in this field. So different kinds, machine learning can mean several things. Different machine learning algorithms can really give you a hand. The machine learning cannot do it by itself, because the machine learning is like a closed, it's a box, right? Once you see the results that the machine learning tell you, you need the expert to say, oh, this is crap, maybe there was something wrong. Oh, this looks like really a signal, astrophysical signal. So that's the difficulty of the machine learning thing, right? So I'm going to show you one example where we're using a machine learning algorithm to help us handle this multidimensional situation. So the high dimensionality of the chemokinematic space requires new statistical analysis methods to be efficient and to constrain better the evolution of the Milky Way. This is the technique we use. It's called TSNE. It's an algorithm that takes care of this multidimensional space and look to all the dimensions and find a map. This is the TSNE map, so the X and Y doesn't matter what it is. It's a unit from the TSNE, and start separating groups the thing. So we throw here 500 or 600 stars with a lot of chemical information and let the TSNE figure out from the abundances if there is something different. And I'm going to show you, it's amazing how it works. Sometimes also how it doesn't work. So the sample that we had is showing us that, for example, there is 2 weirdo stars that do not fit anybody else. There is these triangles. There is these guys here, right? Of course, there is it's a dangerous thing to use because you have to color this point. And how you decide which is a group and what's not a group is the uncertainty thing. And that's where it enters the astrophysical part of it. So let's suppose we believe what the TSNE did. It took our sample from the HARPS and with several chemistry and found this dimensionality and different groups, 100 parsec around us. If we plot those groups in the famous alpha over iron versus iron plot that we are now tired to see, you see that there is the high alphas here. Is telling me, look, the supermetal-rich stars are weirdos. They are not fitting with the others. So it's not like a very simple continuation of this. So you start seeing complexity, even in 100 parsec. Where you say, should I believe this? This is important because usually what people do is that they pass a line here and decide who is high alpha, who is low alpha. In chemical evolution, say this is the thick disk, so I pass a line here. Usually, in the several papers you'll see, using large statistical samples where you do not have all the chemical information, you pass a line, you say, oh, this is thick disk, oh, this is thin disk. And this approach is telling you, be careful. It's not so simple like that. Now, let's see some nice examples. So this is the same thing I show you. And how did the TSNA got this? Of course, you're not supposed to see this, but these are different abundance ratios, barium over iron versus iron, yttrium over magnesium, copper of iron, and so on. And this is over iron, but then the TSNE also look over each other. So that's why you have 20,000 combinations for this data set we had. And the TSNE looked to all that and found this dimensionality. But now, let's take one of them, for example. The first thing from the plot I showed you before, we immediately demonstrated that this high alpha, actually, there are subpopulations there too. And interesting, the high alpha towards the more metal-rich situation seems to be unrelated to the thick disk, but seems to be related to these migrators as well from the inner parts of the disk. So these are like the main conclusions of this paper. But what I want to show you is this example, for example. Let's take barium over iron versus iron. Barium is an S-process element made on longer time scale. When you plot like this, you have a complex thing, but you have this. These stars are there in the middle of this sample, for example. What are they? 100 parsec, okay? So this one, for example, it was a known star. In this volume is one of the highest S-process enriched stars. Then you need to understand why. How come this star is there? It's a debris of something that came from outside. Another interesting pair is the two triangles here. They turn out to be also S-process enhanced because they are high alpha over iron, barium over iron, but they are metal poor. And now, what is nice for this sample is that I could compute the ages with Star Horse, because this sample is in the main sequence turn off. That's what is beautiful. It's not a giant. So let's just look for curiosity. These two triangles, and if you look to them, these are these two stars. The age of both is around 12 gigayears. Two fossil records sitting here next to us, 100 parsec, their chemistry properties are very similar for all chemical elements, you see? That's why TSNE picked them up. And I didn't use in the TSNE, I didn't use any information. I didn't give the machine learning any information about kinematics. I didn't. But then I look a posteriori, what are the kinematics, typical kinematic of the populations that the TSNE broke based on chemistry. And I see different populations also in kinematics, thick disk, thin disk, weirdos, and that's what we see here. The velocities in X, Y, and Z of the two stars are very similar, with some difference here in VZ. And so essentially we found high confidence S-process enhanced stars. It's an old pair, and they also had high proper motion, both of them. So these are two stars that came from another galaxy, most probably a dwarf galaxy, that are here 100 parsec from us. See? That's what I think is beautiful. However, this data set is like the creme de la creme. You have high resolution, you have many chemical elements, you have everything. So, and you cannot be here doing this at 100 parsec all the time. You want to know the full galaxy. So what you have to learn is how to work with less quality and still see, judge if these results hold or not. So we applied this recently, for example, with Anna. Here I'm showing you Apogee DR17, where we use this TSNE. And so we throw our Apogee sample here, But the apogee sample for which we could get age, so the ones that are more in the main sequence turn off, which is a problem because apogee better pipeline is for giants. So we run into other problems. But you see that it has found the two groups here. And when, for example, and when you plot, for example, magnesium over manganese or other abundance ranges, you check where those groups are. And then when you look here, the age for these stars, and for example, the velocity dispersion or whatever, you see that actually you are finding different components of the Milky Way also in terms of stellar population, which means a thick disk, a thin disk, or the so-called young alpha-rich stars. These are stars that have accreted mass from a companion, and they look young, but they are not. It's just that their initial mass was changed, so they look younger, but they are actually old. So the TSNE finds this for me, okay? So this is a way to use machine learning plus this lot of chemical information to find these things. Now, let's go back to the local volume now and go back to this sample that I discussed in the colloquium. So this is a sample using RVS, so the last data release of Gaia, but we have used here another thing with machine learning because there is a different kind of machine learning. This is, we have the spectra of the Gaia RVS. This spectra is a short wavelength range. Then there is a lot of degeneracies with temperature, log G, and so on, stellar parameters, and metallicity. So, but Gaia DR3 had also what we call the XP spectra. These are extra informations that came on a table like as a coefficients. And these coefficients have dependence on metallicity or temperature. You don't know a priori. So you throw these coefficients for the machine learning, in this case, convolutional neural network machine learning algorithm. You go and give that information to this, plus your spectra, and the machine learning will help you, because some of these coefficients depend on metallicity, depend on temperature, depend on gravity, and you have, for this sample, exquisite parallax. So you will have very, very good distance. So this will all help you in your spectral analysis. So if you do the spectral analysis standard, you will need signal-to-noise high. But if you do this spectral analysis with the help of machine learning, you can reach lower signal-to-noise with good spectra, with good output. And that's important because then we increase a lot the statistics of the sample. Because the peak of the signal-to-noise was 25, which is rather low. And a lot of the first works that came out are using spectra that are 200 or 100, right? But there is a lot to tap into. And this sample is special because this is the Gaia RVS sample we are going to use. It's sitting here next to the solar vicinity. You have 170,000 stars within 1 kiloparsecs for which you have amazing parallax radio velocities and also some metallicity and alphas that you can get. And this, I'm not gonna, so this is what I'm showing, the distribution Z and R in the galaxy, so next to us here, and the sun is coming up, there's the sun. And here's the CMD, the log G temperature for those stars. I am exactly in the main sequence turn-off subgiant. We selected this sample is the age for which, the sample for which we can have ages. And then this is how the sample is. Of course, the sample in alpha Iron versus iron is dominated by low alpha because I'm sitting here very close to the midplane. I'm dominated by the thin disk. That's what I have there. So that's what we did. We take the Gaia RVS spectra. These are the convolutional layers that we're going to have. We're going to input as information the XP coefficients that came out in Gaia DR3. We can also put other information that on other photometry that we have. We let this magic happens. This is explained in a specific paper, and we make this data public. We take these inputs now that are better inputs for a larger amount of stars and run star horse on it, the spectroscopic code, and get the ages. Okay, so what did we see? We are today talk about the supermetal-rich stars. So to find the supermetal-rich stars, the stars that are beyond the metallicity of the interstellar medium here today, they are rare, they are not a lot. It's not that you look there and everybody is supermetal-rich. No, you need a big sample. So that's the very good science case for this sample then. So we got here, I'm showing just the number of stars with the guiding radio of the orbit. Remember, we discussed what the guiding radio is. So we compute the orbits, If you have an eccentric orbit, the guiding radius is like the medium point of this orbit. So this star is probably just passing here, but is actually more from the inner galaxy, right? So we compute the guiding radius of the stars and just plot our data. And here is the number of stars we have in each beam, which is already amazing now. We have 23,000 stars between, and we have the metallicity that we obtain with this neural network thing. So minus 0.3 to minus 0.2, so just below solar, this is the distribution. Then you start increasing metallicity. So every plot is the same, but for different metallicity beam, okay? So let's walk from solar, then now over solar. When you pass 0.1 in metallicity, so a little bit more than the sun, you start seeing something happening in the guiding radius distribution. It looks like something's happening. You keep walking in metallicity. Here you already have stars that are reaching between 0.15 and 0.2, so they are reaching the supermeteoroid stars. Now you are in the supermeteoroid stars, 0.2, 0.25, 0.25, 0.3, 0.3, 0.35, 0.35, 0.5. Look what happened. It appeared 2 peaks of guiding radius. So this is to say, the supermeteoroid stars are placed in particular guiding radius. Coincidentally, these particular guiding radius are exactly where the resonances are in our disk, between the disk and the bar. And so it's a way for you to trace where the resonance disk bar is. And this is very important because this constrains the velocity of the bar, the size of the bar, the importance of the spiral arms. I mean, it's really beautiful. And you see that the supermeteoroid stars feel that, and you find that these peaks in this, for example, in this case of this sample, 6.29 and 7.29 kiloparsec from the galactic center, which correspond to what we know nowadays and think are the resonances of the bar spiral arms. So, but the important thing I want you to see of this is that the supermeteoroid stars, the other stars are not telling me about the resonance, but the supermeteoroid stars, they are surfing on the resonance of the bar spiral arm. You see? So they came from the inner. This is another idea, is another suggestion that the supermeteoroid stars are coming from the inner part of the galaxy due to the bar spiral arms resonance, okay? So, and why do we have this? This is a nice review. I didn't put for you because it's really very only dynamics, but essentially galactic disk rotated differentially, right? Where we have in the galaxy a nearly flat rotation curve with a constant circular velocity as a function of galactic radius, but the density waves, which in our case, the asymmetric part of our potential, which is the spiral arms and the bar, they are not like this. They rotate as solid bodies, and that's why make these resonances in the disk in particular place, and they will depend on how the bar and spiral arm connect. So this was just one example of what a supermeteoroid star can tell you. But what we were interested, that was a side effect of our analysis. What we were interested is this. This is metallicity versus age, because now I have the age for those stars. This is not an age-metallicity relation, as I showed before, that is like how metallicity is increasing with age. That's not with time. It's not this. Here I'm plotting only the supermeteoroid stars. So all the stars that are here in this plot, so there are a lot of stars per beam, don't remember exactly how many. So I'm showing here only stars that are above 0.2 in metallicity, the supermeteoroid stars. And then I take at each age the maximum iron for those metallicities. So I have stars that are very old here, and they have already very high iron. Typically of that we saw in the bulge yesterday, okay? And they are old, so they cannot be from here. And then what I'm seeing an interesting thing is that as I go younger in age, this typical highest metallicity that I achieve goes down. But there is one age here that it drops suddenly, okay? What I'm meaning? There are no supermeteoroid stars here younger than X age. And then you say, oh, yes, because if they come from the bulge, they didn't have time to come here, so that's the time it takes for them to come here. No, because the simulations have shown, anybody's simulations have shown that they are able to surf here very quickly. They don't need 3 gigayears, okay? So it's something else that's happening. And our interpretation, and I'm going to show you why, is that the bar formed, so the bar, when the bar buckles, as we say, in the inner parts of the galaxy, generate a very big activity of sending stars at that buckling time. So that is we are trying to constrain the last time the bar was intense. And maybe the bar of the Milky Way was forming and reforming several times. But we are saying here the last time this happened was 3 gigayears ago, more or less. But now we are afraid, as I tell you, because we are using main sequence turn-off stars. So we always, as I said, always look to another data set to be sure nothing is wrong. And we had the lucky situation that we could use the Kepler apogee that we discussed several times, the astroseismic ages. Now, astroseismic ages not in the main sequence turn-off, but in the giant branch. So nothing to do with anything. So two things completely. And here you have a problem that you have less statistics. You have 5,000 stars at most. And when you plot this, you also see the same thing around the same place. Now we say, okay, if this drop in the arrival of supermeteor-rich stars here is due to the fact that the bar buckling time was around 3 to 4 gigayears ago, there are models that say if that happens, you not only send stars here, but you shake the gas in the disk. You put a lot of energy, so you can lead the disk to form stars. If you had the gas in the disk, you're going to have a peak of star formation that's filling this energy that comes. And then we say, okay, is this true? Do we see this? And then we plot this. Wait. Here is iron versus age. But now, not only the meteor-rich stars, all our sample. So we have something old here that's very meteor-rich already. This is the thick disk. Then we have essentially the disk, but we have a blob here. And this blob here is, we believe it is blob, because with the statistic is high, the error in iron is low, the error in age is low, so this blob is there. And what does blob say? Well, a lot of stars around solar metallicity are forming around 4 gigayears ago, 4 to 3 gigayears ago. And here is, again, the alpha Veriron. They are a little bit, very little bit, enhanced, because the alpha Veriron was going down with age in the disk. Here is old, here is young. So the alpha Veriron was dropping with age, as we said, is the clock. But these people suddenly kind of interrupt the drop. Why? Because when you have a burst, you produce a lot of type 2 supernova. And those are the ones that contribute quickly. So you get a little bit enhanced alpha Veriron. So we believe we are seeing hints that the star formation burst happened there. However, there are other works and other groups seeing bursts in the star formation in our galaxy, but they are related to the passage of the Sagittarius dwarf galaxy that I showed you before, that was accreted and made several passages. The point is that this peak here, at this age, is not matching any of the other peaks that are attributed to Sagittarius. So this is also nice, you see? So we say, we think that the bar, the last buckling moment of the bar was 3 to 4 gigayears ago. Well, this is a problem because everybody was saying that the bar was formed 8 gigayears ago. But then we look into why are they saying this, and we didn't find the arguments were too strong. Most arguments were coming from cosmological simulations, which is a problem for the Milky Way because you have problems making bars, and we discussed this already. So we were even interviewed because our bar was too young, essentially our last bar epoch. I'm not saying the bar couldn't form before, but it could. But essentially the last, because there are models also that think the bar form and reform several times. We are just timing the last time this happened, okay? So this is under discussion, I would say. It's a letter for ANA, is accepted, is printout, and so on. Okay. Now we can look to these supermeteor-rich stars that I was telling you in a different way, in beams of metallicity. Each of this is the same thing we were looking. Number of stars versus guiding radius, and you're seeing peaks. And the peaks start appearing only when you cross some metallicity. So here you are not having peaks. At some point you have each are the supermeteor-rich. Same thing we saw before, but now all together. But now you see a second thing. the supermeteoroid stars do not cross 9 kiloparsecs from the galactic center. When you have the other stars, you are still going, but those not. So this limit could be linked to the outer linear blood resonance of the disk. It's the last resonance of the disk where the last supermeteoroid stars are sitting. So this also gives you an important parameter. Here we have some thousands of stars. Now, in another work that we have recently put out, where we use now is a different machine learning algorithm. It's called the XGBoost algorithm for machine learning. We essentially are going to use the Star Horse run to train a machine learning for Star Horse and run over millions of stars that do not have spectra, but have the XP information coefficients, and give me a better metallicity than if I had only Gaia and photometry. And when I do that, and I select the supermeteoroid now over 200 million stars all over the galaxy, here I have, you see, this number, I have 5 million stars now, almost 6 million stars with metallicity above 0.25. And I see again peaks happening here. Okay? So this is what the sort of game. We had thousands, then we have 100,000s, then we have millions, depending on the data set you use to see this. So of course, we were worried that if our metallicities are not good, we would lose these peaks, maybe. But when we saw the peaks the same way we saw in a much better data set, we were very happy. Okay, this is showing you how many supermeteoroid stars are around and how useful they can be to understand things in our galaxy. Now, I wanted to just focus on some, to kind of go towards the end of this chemical thing. A lot of things are happening because the samples are increasing. And a lot of rare things are appearing. So, for example, here in this paper, several abundance rates, so all these points are what we usually see, and suddenly there is this star here. And when you do the spectra of this star, no stellar model can fit anything. So we have stellar models for massive stars, population tree, neutron merge, whatever you want. We check all this, so you don't fit. So these weirdos are very important, because they are the push for new theories of stellar evolution and channels of enrichment of the interstellar medium. So this is, forget this plot now. Then there is another one that is, when you take, for example, nitrogen here. Nitrogen over iron, we didn't talk about this. So this cloud here is most of the data in the Milky Way. Most of the stars we have been discussing are here. But you have a lot of stars here. And there's a huge discussion, what are they? They cannot be dwarf populations because of their characters. The dwarfs are sitting here, more or less. Dwarf, I mean, the accreted stuff that fall in our galaxy. But they are pieces that looks like they are pieces of globular cluster debris. As you saw from Beatrice Barbuy, the globular cluster, as we said, is not a simple population, has double populations. And this globular cluster, when they are next to the bulge, they are disrupted even more easily. And now, when you look into apogee, that you can go to the places where there is a lot of baryonic matter, so disk close to the midplane and bulge, you start seeing disrupted globular cluster. And then people start discovering what we call very high nitrogen-rich stars. And they are apparently pieces of globular cluster around. So you want to have also this complication in the middle of the story. And you have nitrogen-rich, some aluminum-rich stars, some silicon-rich. These stuff that are outside of all the clouds we are analyzing. So then there's a lot of motto to understand nucleosynthesis in different situations. Here is a very interesting one. This is phosphorus. And there is a group of stars very high in phosphorus here. And people don't understand very well how. And these rich phosphorus stars seem to correlate also to silicon, which people also don't understand how. I mean, this is really like crazy. This is another abundance ratios, and you see this crazy aluminum-rich, oxygen-rich, magnesium-rich. I mean, these things, and then nickel normal. So, and then people go analyzing each element and plotting these curves that you see here are different chemical evolution models. White dwarf, type 1a, supernova with rotation, supernova with whatever. There are the flavors that you would like to have, they are there. So, I want to conclude this part by saying that we have amazing data, but now we have main challenges. And I put a list of some of them. So we are having, every time, more statistically significant rare samples, samples of rare stars. Well, if you find one, okay. If you start finding many, it's not so okay, okay? So it requires some explanation. And also we are finding some of them in previously unexplored regions of the Milky Way. Because now we can go to the bulge. Now we can go next to the midplane of the galaxy. So now we can go very far in the halo of the Milky Way. So there's where we are also finding a lot of this. So that means that we need, many times, new stellar models beyond the standard cases. You know, when people have to give money to research, it's always said that stellar evolution, we know everything already. It's not true. It's exactly now that you're going to need a stellar model very good to address these kind of things. And everything is, you know, it's like the card castle. I mean, stellar models, the star is the base of everything, of your integrate spectra of whatever you do. You need to understand the stars. Another one is that you can then test different scenarios for the time scale of type 1a supernova. We said type 1a supernova is a binary system. We still understand nothing about binary systems. So that's very important. Binary systems in general, neutron mergers or white dwarf with red giants, all this. We have also to, as I gave you a hint to you, we have to be able to extract the most we can from large data sets. But there is not so good signal to noise. Well, it doesn't matter. The data set's there, has huge parallax, have fantastic orbits. You have to be able to work with this data set. You're going to use machine learning. And machine learning is a big name for things that are changing every day. Today is convolutional network, XGBoost, TSNE. I show you some. Tomorrow is something else. So that, I have to say, is the young people that are with the hands on. I mean, my students, when they come with different algorithms, sometimes I have even tough time to understand what they're talking about. And then, but to analyze the output of that, we need to do this together, okay? So it's very important to look to this. And we are seeing stars here that are born far away, as I show you. And this is complication, but it's also a gift. Because you have two stars, the pair of stars I show you, from 12 billion years ago in another galaxy. With that pattern of chemistry, you need an ELT and a very lucky situation to find them, you know, and we just found them here next to us. So this is now is very nice. So we need to invest in stellar evolution theory. That means we need to invest in people. We need to deal also with advanced machine learning methods to address the large database. And we need to understand and include the evolution of binaries. Also, the data that I'm analyzing, the spectroscopic data that when I show you the CMD, I'm ignoring that I have binaries there too. So sometimes star horse can go wrong because actually the luminosity is the two of them together, and I'm thinking is a luminosity of one star. Distance will be wrong, okay? So this is things that have to be addressed. Okay, now the challenges are there. And I will finalize by showing you some what's next. So everybody is knowing the challenge. We know the limitations of the data. And you also are having these big groups, big collaborations. And especially the young people sometimes are like, oh, I'm not going to enter in this collaboration, spend too much time in these meetings, in these Zooms. I don't have a permanent contract yet. That is not the way to go. The way to go is to enter, to join, and to protect yourself a bit, or join with somebody that can protect your time, but join, because these big collaborations is the place where you discuss the big questions and you meet a lot of people, right? So I'm going to tell you what's next. Next for me, unfortunately, but for me, my time is taking here, the foremost thing. So we started prepare, when Gaia was going to fly, the ESA and ESO form a committee here to discuss how can we prepare the spectroscopic follow-up of what Gaia will give. And this was done here in 2008. We wrote this book, like 77 pages, to say what we need. And at that time we said we need multi-object spectroscopy in 4-meter telescope. We need a mission with astroseismology that is beyond Kepler and Corot. We have Plato, we have Formost, we have Weave. These are the things that are born from this kind of documents. Not only this, but also roadmaps that Europe say. And then when the first, for example, the first release of Gaia, that immediately they found the Gaia Enceladus in our galaxy, that we had this collision, they needed Gaia, but they also needed the spectra. They use also, to confirm their thing, they use apogee spectra. So it was clear that this is needed. So essentially what we are saying before is that we need to, the legacy of Gaia will need radio velocities and chemistry, and we need to get prepared for that. And then we have foremost, which is in the south, Weave in the north, Sloan 5, north and south, all of us taking spectra more or less at the same time to cover the full sky with spectra. Okay, so timescales. We are here in 2024. Let's see what's going to happen between 2030 and 31. There will be a transformation of the Milky Way and other galaxy data. I already showed you some happening. And spectroscopic surveys will go to a next level than what we are. It's going to go to a next level than what we are doing now that will start next year. So that's the difficulty, you see. We are putting all our time on something, but we already know we need more, even before we start. And who are going to write those documents? We. So we have to do our survey, write the document, and it's our generation. So that's why the next generation should take leadership, otherwise the things die out. So here I'm focusing on European lead projects. So here, foremost, that I showed you before is this multi-object spectrograph that goes to the VISTA telescope, 4 meters. Then WEAVE, the telescope, also 4 meters, slow one. And MOONS. MOONS is in the, going the infrared, and it's going to see the bulge, but the field of view is smaller, okay? So all this is starting here, 24, 25. We all got delay, so it's around here. Then the ELT first light will happen here, the extreme large telescope, okay, from ESO, will happen here. And there you have 2 spectrographs, very important, the Mosaic and Andes, that are now consortiums to build this up. We are in 2029. Now, on the top of that, you have the astroseismic missions. We had here, we are using still data from Corot, Kepler, K2, and TESS. I didn't talk about TESS too much. And Plato will come out in 2026. Okay, so that will be astroseismic to combine with spectroscopy and do what we are doing for small sample stars. And in the top of that, here down, you will see Gaia. Gaia DR3 was in 2023 to 24. RVS, the spectra from Gaia became available, but this is spectra that you have to do all these things to use it. And then Gaia DR4 is scheduled to 2026. So we are going to get crazy, because we are going to get DR4 at the same time we are having to prepare maybe the first release of foremost. Then the next release of Gaia, Gaia DR5, it's going to be around here. There, it will be amazing. I mean, hopefully I'm still on the game. And so what do you have? During this time here, up to 2027 or so, we have huge discovery space, just like the ones I show you with some spectroscopy. Discovery space is like discovering new things in the galaxy. And this is illustrated in this time most, 2010, 2020, the results I show in these lectures. And using surveys in the optical and the near-infrared. Now, by here, we will increase the volume with high-precision data. It will be a huge follow-up of the discover stuff made here, okay? And we will go from multiplex of hundreds to thousands. That's what we do here in Formosa. So the surveys I show you, like Apogee, Rave, and all those, have hundreds of fibers, 300 fibers, for example. Foremost, and we will have thousands of fibers. So we're going to jump from hundreds to thousands now, and then we're going to jump to multiplex of 10,000 to 20,000 fibers. In one shot, 20,000 spectra, right? It's trouble. I can tell you, it's trouble. Because you have millions of spectra, either you know what to do with machine learning, or we have trouble. We're going to have trouble here, right? That's why I'm putting myself into this game, so that we can analyze the abundance of our survey, right? Then, I told you, Gaia infrared and WST are being planned. We are writing the documents now. There are 2 white papers on this. It's in the list of material I gave you. that came out, one in 2021 and one in 2024. So Gaia infrared and WST. What's WST? We're going to see in a while. 12-meter telescope. It's not only the instrument that they want to build. They want to build the telescope for doing spectroscopy of IFU and multi-object spectrograph. So integrated field spectroscopy like MUSE, but also spectroscopy like we are doing with this other data that I show you. This is me dreaming that one day we will also have isotopic ratios, but for now, forget it. Okay, so as I said, the community always start preparing before. The same way that in 2008 we were discussing these things. Now we have a call, we had a call for ESA missions, satellite missions, for the future. So that's why it's called, this call is called Voyage 2050. Meaning, we are now discussing the instrument that we want to have by 2050. Who is writing? Us. So when you are around your 50s, or let's say, I say 50s, but yesterday I just made my 56th turn on the Earth, you are going to be doing other, so you see, oh, my PhD is so difficult to manage. No, it's the whole time like this, you see? Because now you're managing the survey and the document of the future missions and so on, so that's what's going to happen. So here, we did a huge job to push for 2 missions. We were selected the 2. The Hayden, which was doing astroseismology in dense fields, and the Gaia infrared. The astroseismology in dense fields died, because at some point you die. You do a lot of work, you die. It's there. You know, one day maybe we put it back. But Gaia infrared is still there. So they made the call, and then they put out the seniors report where they say, we need that, but in a very elegant and vague way. And this is what's written here. We need a medium mission design to carry out pure astroseismology that would characterize stars in a wide range, relatively homogeneous stellar environments. This was, for example, our Hayden. Astroseismology in clusters, astroseismology in dense fields, astroseismology in the bulge. It's coding here. Then we need missions that would provide key information on stellar physics and would allow also testing in stellar evolution models, is that. And then furthermore, and in combination with Gaia, a large ground-based spectroscope surveys that would also need, and so on. They start discussing what is needed. So among of them, Gaia infrared. This is the number of stars per square degree that we believe we have in our galaxy. And Gaia infrared is, as I said, in this, we discussed this in this paper here, where we have our white paper. White paper means when you're designing something that maybe is going to happen, it's called a white paper. Then, here we are plotting the number of stars that you expect to see in infrared divided by the number of stars that you see in Gaia. Of course, here is where you're going to see 8 or 10 times more objects than what Gaia see today. So you're talking about a Gaia that will not have 2 billion stars, but will have 8 billion stars, okay? That's what could be. But can I say 8 billion? This is science already. I don't know if it's 8, 6, or 10, you know? This is part of the science. So Gaia infrared hopes is to probe the regions, the inner regions of the Milky Way, so there, where it is red, to improve the proper motions for the Gaia itself. As we discussed, the proper motion needs baseline. If I had made exactly the same Gaia in 2050, I would have a huge improvement in proper motion already, but it's very difficult to sell an exactly same instrument 20 years after, okay? And also reset the optical reference frame, forget it. Okay. Here we show, for example, our Star Horse run, the big run we made that I have been showing you, but for where we have good data. And this is showing you where Gaia is not working. Everything that's yellow here, with the current Gaia, I have trouble, because either I don't have data, or the parallax is bad, or I can't, you know? So that's also to justify, look all around, and you see some dots here. These are clusters. They are too crowded for Gaia right now. So that's where you're not going to have good parallax. You're not going to have good proper motions, and that's why we need Gaia infrared. Okay, so where are we? 2010, there was an initial proposal. 2020, a concept developing the proposal, because they tried here and was not possible, so they retry. We retry now. I was not in the first, I'm in the second, just like Hayden. In 2030s, we should have a detailed design mission already and acceptance, and then to be launched in 2040 or 45, okay? And then we can do the bulge and inner disk part with improved proper motion and, oh, what we dream of. Let's see what's going to happen. Okay, but before that, we have now, next year, foremost with moons and Sloan 5 is picking up. It's already started. So we will open here interesting regions that we will focus then after with ELT, because these here, they are wide field. So you see big in the sky. In the ELT, the field will be small. So you better know what you want to see already, because it's a 49-meter telescope. So you're going to go very deep, and you need to find the right targets, because you're not going to be sitting there well, anyway, obviously. So where to focus, how to connect the properties we see in the nearby galaxies by using MUSE and the integrated field with what we see in our galaxy. Okay, the formidable OR is our survey in the bulge and disk of the Milky Way, where I told you we are covering this in X and Y. If you're looking at our galaxy from above, here most of the spectroscopic surveys are here, and we are supposed to cover the inner disk bulge part of the galaxy with spectra. I had explained that we have more or less a extended solar vicinity. Here's where the best of Gaia, DR3 and DR4 are sitting with good parallax. We are going to have this big sample, which is called bulge inner galaxy sample. Here's the bar. And we are going to have a more sparse sample with two different signal to noise, one to get chemistry and one to get only kinematics. But maybe we even get chemistry depending how we handle machine learning. So projects are made of people. We have telecoms. These are some of the people. In our survey, we have 60 people. These are researchers in other institutes that are helping, you know. Nobody's paid for doing anything. It's really like you rely on people doing this. And we are very thankful, and we try to keep good mood when we are working, because sometimes we have stress, of course. But the good mood is part of our main point here. So we had, to arrive where we are, we had milestones. There was Gaia DR2. In 2019, we start preparing this when we start running Star Horse. And there is this paper that I just showed you in Messenger where we present this survey. And essentially the problem we have is how do you select the best 10 million from 2 billion? Because I also have a budget of fiber hours that I can use. And it's not much. I mean, it's a lot, actually. But we always want more. And so how do you do this? And that's why we have 4 big catalogs. Because if we just go there and take a bunch, we end up with a lot of stars here again. You know? So we need to do this ESN, DIM, CHEM, and BIG that I just showed you. Then we need to add our very important calibrations. Now you understand what this is. Seismic giants. We need to also get spectra from the targets that we know have astroseismology, because we know a lot about them. They will help our pipeline. So we need that. We need clusters, because they are always holders. We need also a deep view in the bulge. So there will be another bulge deep, and the leader will be Anakeros. And we need to also lead and look for the very metal poor stars. Here I discuss more the metal rich, but we need the very metal poor as well. And the metal poor stars, they are not here a lot. You have to really to find them. And to find them, we are using Gaia, XGBoost, machine learning to see who is metal poor and make amazing maps of candidate metal poor stars. They are candidate, but we need to get the spectrum. Okay. Then we had, at the same time that Gaia is happening, Sloan was having the release, and Apogee came up. So when Apogee came up, we could really see this plot that I show you, the extension of alpha over iron versus iron in the whole disk, which is this paper. To see and what? To proof of concept that we are able to obtain distance in very high extinction situation at the level of 10%. That was a proof of concept. Of course, there is the science of this paper, but it's also a paper for proof of concept that Star Horse was working fine. Then, in 2020, we had to write really the proposal for pre-proposal to ESO for our science. And then we could add the ancillary science. Because imagine, I am sitting on this disk doing with 2,000 fibers. And then I have a group that have white dwarfs here and there. Well, we can take their spectra for them easily, you know. So these are called ancillary science. Science that do not decide where I go, But once we decide where to go, we can do their science too. It's science for free, essentially. And then we had really to write the serious proposal to ISO. This is end 2020. And then we got also the possibility to add all these ancillary science. Cepheids, on our footprint, we're going to have planetary nebula, cepheids, white dwarfs, hot subdwarfs, very metal-poor stars in the bulge. These ones are come from eROSITA survey, where we have also compact white dwarf binaries, and so on. So each one has a sub-survey leader person. Then we had Gaia EDR3, which was end 2020. And then now we could do another thing. We could run the star horse that I showed the results here for you. And then we could show that we can trust our extinction maps. That's what was the goal. And then we had the Sloan DR17, which is amazing, where we finally could enter in the bulge, because DR17 had also the southern apogee data that I show you. We could go to the bulge. So we did the science here in the bulge, but we also checked Star Horse and got a good result. So finally, we are, the ISO gave our consortium survey 70% of the fibers, but 30% of the fibers, because the institute is building with these other collaborative institutes, 17, I think, institutes. But then the community has also the right to have their own surveys. So the community apply, and the best surveys that match better our survey strategy were selected, and that's when the community survey people join, and then they join. So today we are 700 people in the foremost collaboration. And then after they join, we had Gaia DR3 that we were, whoops, what happened? And then we enter in this optimization phase. We are getting ready, and then we are on the sky. Here, I didn't update, it's actually 25 to 29. Okay, so what are we going to see? This is X and Y for a catalog or DIM. This is how our catalog we put as input, and they do not observe. So because now we have simulators that have to simulate all the catalogs. So, but we are getting out the successful targets observed with this X and Y distribution, Z and R distribution that you're seeing here. So we are covering the disk, and then we have other samples covering the bulge. Important point of foremost, especially my survey, is that we are doing with low resolution, but the spectra go from 4,000 to 9,000 is low resolution, but in this spectra you have several lines. So these are the lines of the chemical elements you see. They are low resolution, so you need to know how to make a pipeline work with that, and we are publishing papers using this CNN that I told you and stuff to test pipelines on low-resolution spectra to see if we're doing things well. Okay, in the bulge, the reason we are discussing yesterday, this is a box of 20 degrees. This is the big Blanco survey, that is the DECAM bulge survey. It's a photometric survey led by Mike Rich, and this is their footprint in the inner part of the galaxy. Our bulge survey will cover this, the big survey will cover that big thing. And in the inner part of the bulge, this is the box with the extinction we discussed yesterday, where the globular clusters were. The BDBS that I just show here, so here's a zoom of this here, that region. And the BDBS is covering this footprint with only photometry. And we are covering this footprint also with the bulge deep of where Anna is the leader, where we're going to get spectra for stars in this field. Okay, that's foremost in 2 seconds. And that's our foremost, the part that we are doing. Now, I will finalize just with this. We will have also, hopefully, this is starting, is a white paper. The idea is to build a 12-meter telescope. And this is a joint between the galactic and the extragalactic community in Europe. And the white paper just came out, and essentially they have this figure where essentially all the science that the wide field spectroscopic telescope will do goes from cosmology up to the galaxy and nucleosynthesis. So it's almost like this school, you know, like we have everybody on the same boat. We have to talk. And what is this? This will be a telescope with a 12-meter telescope with a large field of view, that's important, with a 3-degree field of view, which will be missing for ELT, VLT, so that's complementing. We're going to have the multi-object spectrograph based on fibers, like we are doing now for most, but we are also going to have the integrafuse spectroscopy, like, for example, MUSE. I think that's most, so we're going to have MOS low resolution, MOS high resolution. Here, the resolutions are similar to FORMOST. We are discussing that, 4,000 to 40,000. Here, people are pushing more because in FORMOST, the high resolution mode is 20,000. And this is the amazing thing. Multiplexing, as I was telling you, 20,000 fibers, okay, in this low resolution mode. Now we have 2,000 fibers, okay? So that's a lot. That is also nice, the field of view here, comparison with ELT, you see, the field of view, VLT, the field of view, and this sort of field of view is what you need. And that's why you need to build not only the instrument, you need to build the telescope. And that's the project. Okay, so I will finalize with my favorite thing, the Milky Way. I hope you had fun. It's an amazing time to be an early research. It's an early career research. Yesterday, as a birthday gift, I got this card from my daughter that she painted, and she was afraid that I wouldn't recognize what she was painting. I said, okay, I think I did. Very nice. And the lessons I think I have learned in these many years, I'd say, is very simple. I mean, enjoy while you're doing it. Do not always like, oh, I don't have permanent position. Enjoy now, because every moment is a moment. Do not lose your curiosity, even when things are complex. Keep curiosity on, because it's that drives your questions and drive your decision. Which is the project I want to go? Because you can do 100 things. Which is the next point? Why we are going here first? So that's curiosity. And work really hard, because unfortunately that's the way we do work very hard for very little money. So I thank you very much for the attention, for the patience, and for being here in the last lecture of the last day. Thank you.
Okay. All right, guys, questions?
Thanks for the lecture. You talked about if you can...
Yeah, tell me what.
The survey, WST.
Yeah.
For extragalactic. Yeah, is this a spectroscopic survey,
yeah,
right?
Yeah, spectroscopic survey, yeah.
And it will start in the next year?
No, look where... No. That's another, is a point that I want to make. So right here. Now, where is it? The time scale. It's 2030 if. I mean, where are the time scales that I put here? Here. The WST is there in the 35s.
Ah, okay.
Now, be happy, because you can still decide how it has to be, you know. Mm-hmm. So this is the thing. Every project, as I told you, to get FORMOST starting now, I was the project science of the whole FORMOST. I was project science in 2010. What did I do? The beginning of FORMOST, I had to define what is called the design reference surveys. Why you need this telescope or this instrument? Because you have to do something that the other instruments cannot do. By the time it's up. So 10 years before, you have to know what are the problems, what the others cannot do, why you need FORMOST, you know? And the same thing, and then you need another 10 years to build it. That's the time scale, 20 years. So there's a career for each instrument. The people from Gaia, they work their whole lives. And so now you want a WST, it's not coming for free, because there are a lot of projects. So we're gonna have to fight for this. So we started. We think we need that as a community join also. You want to join with cosmology, galaxies, and us, right? You want to be a big group. And then we write the white paper I told you, but maybe it's going to come here. 2035, I go in pension, if I keep there. But hopefully I find another institute where I can work a bit longer. That's the time scale.
Okay, thank you.
Just checking, it's going to be in Chile, if it is.
Yeah.
WST.
I just wanted to add that WST just got a 3 years grant for being studied, to do a concept study for WST. So that's why we need new minds and new hands to work on the development of WST.
Yeah, and only got that because the group wrote a proposal, and before writing the proposal, need a white paper out. So you see, the time scales are pushing because of that. But it's a very good news that they got the proposal to start the studying phase.
More questions?
Are you guys in WST? You? Oh, time to join. No, I'm kidding.
Okay, so regarding the graphic that you showed us, showing the supermeteoroid stars and the guiding radius.
Yeah.
So you said that those supermeteoroid stars are in the bar and they're migrating, right? But I'm guessing that they're not the only stars in the bar. So,
no.
Yeah. So
exactly.
Why?
Yeah.
So why? Yeah. Are they more likely to migrate?
No, because you saw from last lecture that most of the stars, the reservoir of stars that are ready to migrate are in the bar, in cold orbits, very in the inner parts of the galaxy. And there I show a metallicity distribution where there was a huge peak at high metallicity, but there was a tail for low metallicity. They maybe are there also, but you see, but the huge amount is those, and they stand out because they are they have too many metals to be forming here. So those ones I can immediately say, you know. If I put everybody, the signal is less clear, as you saw. You don't see much of the peaks if you put everybody together. That's the reason.
Okay, thanks.
That's why I need to show the bulge before I came here to this thing. Yeah.
So you were a bit vague about when Formos is actually going to start.
No, June 2025.
June 2025, okay.
Maybe September.
Okay, I will not ask my question after this answer. All right.
Is you know.
Oh, yeah, I see. Oh, of course. We'll talk later. More questions, people? Last questions of the school. Well, not last questions. We'll have a closing presentation here, but okay.
Can you explain just a little bit about the first machine learning that you talked about, the TSNA?
Yeah.
It's what kind of machine learning?
It's an algorithm that you can even run very quickly in Python. It's ready for you guys that like Python. It's essentially something that's gonna. The difficulty of TSNE is that you give a lot of information and they have to be normalized. You cannot give something that goes from 0 to 10 and something that goes, whatever quantity it is, from 0.3 to 0.2. I mean, they have to be more or less same order of magnitude. That's why using abundances altogether makes sense. Abundance ratios, essentially. Essentially, this is a method to check distance between information. You can use that for several things that people have used even during COVID to see things. But so it's any data set for which you wanted to find weirdos inside the data set. So that's why it's a reduction of dimensionality. You reduce all these 30 more dimensions into 2. And this is projecting those diagrams in clouds, in islands. No? The difficulty is to interpret those islands because I paint them. Then in another paper, I painted them because the data of chemistry was very good, so we could see where they were in different chemical plots. In the second data set of Anna, which is the KDOS 2023 paper, as we use data sets with less quality but larger statistics, then we use on the top of TSNE HSB scan, who can found the clustering in a distribution and try to do this more without me having to add to say this is an island, that's an island, without me having to color anything. There are difficulties, there are limitations. That's why it depends on the data, you change your machine learning approach you have. And of course, we tried hundreds of things before. And actually, I had used TSNE before with another postdoc When we had in the beginning, in the 2017, is Matijevich, Chiappini et al., 2017, we had used it on spectra. He took the spectra, and the spectra could find from the pipeline who was metal poor. We were looking for metal poor stars in RAVE to do spectroscopic follow-up of these metal poor stars to see the early universe and so on. And it was difficult to find because of the difficulties in the RAVE pipeline. So we used TSNE to stand up. This is a little island where we see very metal poor stars. You know, some spectra, we had good spectra. They are also there, so you can figure out. So you can use on spectra. You can use on abundances. You can use on kinematics. We run TSNE with the kinematic information, without the kinematic information, with the age, without the age, with 10 elements, with 5. You know, and it's a lot of work to get to the final thing.
I'm curious about the WST. So how deep is it supposed to get? I mean, say for stars, and the targets are going to be selected mainly from Gaia, or
the targets are going to be selected mainly from Gaia.
Mainly from Gaia.
Yeah.
So,
because
but Gaia. So the question is, I mean, Gaia can go relatively deep, but not. I mean, I suppose that WST can go much deeper than the depth
but for
of
stellar,
Gaia.
you're saying for stellar. Targets,
yeah, well,
because for galaxies, yes, you can go deeper. But for I didn't put it here. I have another one because I turn off this. Didn't want to show it. Is this one? Yeah, I didn't talk about, but you're also gonna have the photometric deeper surveys, LSST, Nancy Roman, and there you're gonna go deeper with proper motions and so on. So you're gonna have also this, you know.
You can have a deeper sample from the other surface.
Yeah,
right.
so yeah, you have enough targets.
No, for sure you have enough targets just for
interesting targets, let's put it this way.
Anything else?
I took this out because this was when we are still in the Haydn option, which got cut by ESA. That's why.
Well, okay, so then let's take Cristina again.
Thank you.